So the two herders decide how many sheep to graze on the village commons, which is small and can be overgrazed. Now QI, I is equal to 1, 2, is the number of sheep each herder I grazes on the commons. And the per sheep value of grazing on the commons, so every sheep can generate wool or cheese or milk or even meat. So there's a value attached to every sheep. And that value is given by V, which is a function of Q1 and Q2. Q1 is the number of sheep which herder 1 brings to the field, and Q2 is the number of sheep which herder 2 brings to the field. And V of Q1, Q2 is equal to 120 minus Q1 plus Q2. And note that V, the value, falls as Q1 or Q2 rises. So in other words, the value which the herder obtains depends not only on his own sheep, but also on the number of sheep brought in by the other herder, right? So the other person's actions also affects your outcome. Now in this situation, a matrix cannot be used to represent the normal form of this game. And the normal form is simply a listing of the herder's payoff functions. So let's see what the payoff functions are. The payoff of each player is the quantity of sheep times the value per sheep. So we have the payoff of player 1, U1 of Q1, Q2, that is equal to Q1 times V of Q1 and Q2. So that is just equal to Q1 times 120 minus Q1 minus Q2. So Q1 multiplied by V. So when I remove the brackets, when I remove the brackets from this expression, I have 120 minus Q1 minus Q2, and that's what I write over here. And similarly, the payoff of herder 2 is equal to Q2 times V, and that's equal to Q2 times 120 minus Q1 minus Q2. Now to find the Nash equilibria, we solve each herder's value maximization problem. So we solve them separately. So let's solve herder 1's value maximization problem. So herder 1 will maximize by choosing Q1. Remember, even though the herder's value depends on the number of sheep brought in by the other herder, he himself can only control the number of sheep he brings to the field. So when he's going to maximize the value function, he will choose Q1 if he is herder 1. The first order condition is you differentiate V with respect to Q1, you differentiate U1 with respect to Q1, and you get 120 minus 2Q1 minus Q2, and you set it equal to 0 because we are maximizing. And from this equation, we solve for Q1 and we get 60. Q1 is equal to 60 minus Q2 by 2. This is the best response of herder 1 as a function of Q2. So this is the first step in our analysis. Similarly, by solving the maximization problem of herder 2, you will get Q2 is equal to 60 minus Q1 by 2. So remember where this equation is coming from. This equation is coming from the payoff maximization problem of herder 2. So herder 2 solves del U2 by del Q2 and sets that equal to 0. And from there, he obtains Q2 equals 60 minus Q1 by 2. So the Nash equilibrium would be the pair Q1 star, Q2 star, which solves the above pair of best response functions, right? And you solve them simultaneously. You will get, and you can solve them simultaneously in any way you wish. What I am doing is I'm plugging Q2 into Q1. So Q1 is equal to 60 minus half times 60 minus Q1 by 2. And from this equation, you can solve for Q1, and you will get Q1 star is equal to 40. And similarly, you can solve for Q2 star, and that would be equal to 40 as well. So in the Nash equilibrium, each herder grazes 40 sheep on the commons. And we can actually solve this algebraically. You can solve this graphically by drawing the best responses. And here we have done so. Notice where the two best response functions cross each other or intersect each other, you get the common values of 40 and 40 for each, right? That's the Nash equilibrium, point E1. Now notice, even though we have calculated a Nash equilibrium, it actually does not represent the best use of the commons. Now, instead of maximizing the payoff functions of each herder separately, we can look at a joint value function or a joint payoff function. So we have Q1 plus Q2 times V, and that's equal to Q1 plus Q2 times 120 minus Q1 minus Q2. Let's solve this for herder 1. So we maximize it with respect to Q1. And your first order condition will yield 120 minus 2Q1 minus Q2 minus Q2 is equal to 0. And from here, we can get the expression Q1 plus Q2 is equal to 60. We are unable to obtain a single value for Q1 or Q2, okay? So in the solution, any values of Q1 and Q2, which sum up to 60, will solve the joint value problem. So if Q1 star is equal to Q2 star is equal to 30, that could be a solution. Or Q1 star could be 40 and Q2 star could be 20, that could be another solution. Or Q1 star could be 0 and Q2 star could be 60, that could be another solution. Any situation where Q1 plus Q2 is 60 would be a solution of this problem. Now, how is this solution different from the previous Nash equilibrium solution? In the joint value problem, which we just calculated, a total Q1 plus Q2, a total of 60 sheep would be grazed on the commons. Whereas in the Nash equilibrium solution, where Q1 star was equal to Q2 star was equal to 40, a total of 40 plus 40, Q1 star plus Q2 star is equal to 40 plus 40, which is equal to 80 sheep would have been grazed. Now, from the perspective of common resource depletion, the joint value result is superior to the Nash equilibrium result, which was calculated on the basis of best responses, right? As a fewer number of sheep would be grazed. So in the joint value maximization problem, we have a total of 60 sheep. In the Nash equilibrium solution, we had a total of 80 sheep. So 60 sheep is better than 80 sheep from the perspective of common resource depletion. The fewer number of sheep you graze on the commons, the less likely it is to be damaged. And the more sheep that you graze on the commons, the more quickly it is going to become depleted. So this result is sort of similar to the prisoner's dilemma, where the Nash equilibrium outcome, which was betray and betray, if you remember, led to a lower payoff than silent, which had a higher payoff. So betray, if I remember correctly, had a payoff of 1-1, whereas silent had a payoff of 2-2. Please confirm this. So the tragedy of the commons shows that the feature that the Nash equilibrium is less efficient for all players than some other outcome. So I'm going to stop the share here.